let's talk about the subatomic structure of the atom and also isotopes. So looking at electrons, protons, and neutrons, first of all, take notice of their abbreviation. So electrons have this little E minus, protons a P plus, N is this little N naught. As far as the charge of an electron, because it's a relative charge, we say it's a -1, and a proton would be a +1, and a neutron would be neutral. When you see the mass, this is the real mass. You don't need to know that, but you do need to know the relative mass or the atomic mass unit mass. Electrons do have a mass, it's right there, but in comparison, this is super tiny. It's 1/2000th of a proton. And so because the mass of a proton is 1 and the electron is so small, 1/2000th of a proton, we say it has a mass of 0. But it does have a real mass, it's just super small. A neutron also has a mass of 1. So in the nucleus are protons and our neutrons, and that's where the mass of the atom is. And outside the nucleus, that's where the electrons are. Electrons are responsible for electricity, electromagnetic spectrum, which we'll talk about later, chemical bonding. Protons identify the element. It's the atomic number is the number of protons, and it's the big, large number in each box of each element on the periodic table. The neutron helps binds the protons in the nucleus and keeps the nucleus together. So most of the mass is in the nucleus and most of the volume of the atom is in the electron cloud. So looking on the periodic table, we have the atomic number. It's also given the Z number. That is the number of protons. We have the element symbol. Remember, the first letter is always capitalized and the second letter, if it has one, is lowercase. And then we have the atomic mass. It's the average atomic mass right here, this decimal number. Now compare this white box with the other one. This is a nuclear symbol and it's for one atom. This over here is for all the atoms. Let's look at the nuclear symbol for one atom. So we have the mass number is a 4, and this is determined by taking the protons and adding it to the neutrons. The proton number you always can get from the periodic table. You can just look it up. You can look and see there's the atomic number, which is the number of protons. So again, this is the nuclear symbol that is for one atom. Your mass number should be a whole number if it is just for one atom. So just to sum up, in a neutral atom, the protons equal the electrons. That means the positive charges equal the negative charges. And the atomic number equals the number of protons and also equals the number of electrons. So in a neutral atom, if I have 5 protons, so if I had boron, the atomic number would be 5. I would also have 5 electrons to cancel out those 5 protons. The atomic mass, as I said before, is protons plus neutrons. The average atomic mass, it's a weighted average. So some atoms of the same element, they might have different number of neutrons. Same number of protons, but different number of neutrons. And that's what an isotope is. And because of that, it makes the average mass not a whole number. That's where I get that decimal number, because it's a weighted average. If you have just one atom and you want to tell how many neutrons it has and how many protons it has, you just put the mass number with the symbol. So helium-4 is what I have right there. So it has 2 protons, 2 neutrons, and I would describe that isotope or that particular atom as helium-4. All right, I alluded to isotopes. Let's talk about what they are. Here I have 4 carbon atoms, and I know that they're carbon because they all have 6 protons. 6 protons always means carbon. But look, this first one has 6 neutrons. This one has 7 neutrons, and the last one has 8 neutrons. And so the carbon 14, this one is going to be the heaviest, and this one's going to be the lightest. And so when you look at carbon and what its average atomic mass, you see that it's 12.011. So because of that, I know that most of the carbon in the world is this carbon 12. So very little is carbon 14 and carbon 13, but it is present, and that just takes the average a little bit above 12. And notice it's a weighted average. So if you have, in this case, a lot more carbon 12, that means the average atomic mass is going to be closer to the 12. Calculating the average atomic mass, it's also called the atomic weight. You take the isotope mass times the abundance plus the isotope mass times the abundance and keep it as a percentage. I find that students make a lot of errors if they take it out of the percent. How we'll take it out of the percent is at the end, we'll just divide by 100. So I have magnesium here. There's a typo. So I have 3 isotopes of magnesium, magnesium 24, 25, and 26, and I have their abundance. So I'm just going to use this formula. So take the isotope mass, so the first one is 24, and I multiply it by 78.99, and then I'm going to add it to the next one. I have 25 times 10%, and I add it to the next one, which is 26, and 11% of a sample is that magnesium 26. So I keep it as a percent, and then I'm going to divide by 100. So when we do the math, I get 24.32 atomic mass units. And if you look on your periodic table, you'll see that we're pretty close. So in a certain sample, you're going to have magnesium 24, 25, and 26. And to find the average, it's a weighted average. So again, multiply the isotope mass times the percent abundance, and then at the end divide by 100, and then you'll get the average atomic mass. Ions. This is an atom with a charge. Metals lose electrons and nonmetals gain electrons. So when you gain an electron, that means you'll have a negative charge. And when you have a metal cation, if it loses an electron, it will have a positive charge. Look and see what happens to the size when it gains or loses. So this one right here loses an electron, and you can see the size goes down. And that's because the number of protons stay the same, and because there's less electrons, there's those protons pulling on the electrons, the nuclear charge stays the same, but there's just less electrons to pull in. And so because of that, it makes the ion cloud smaller. And you can see that with all of these. When they lose electrons, they're going to get smaller, their ion. Losing 3 electrons with this, you can see it get really, really small. Let's look at our nonmetals. They gain electrons, so they'll come from a metal, and you can see the electron gets larger. So the nuclear charge is the same. So selenium ion and selenium atom both have the same nuclear charge or number of protons that can pull. It's just because there's more electrons, you get more electron repulsion, and the atom gets bigger because of that. So looking at this chart, you should know how to fill it out. So I'm just going to fill it out with you and talk it through with you, but if you think you know how to do it, you can stop the tape and practice, or you can get your packet out and there's a problem that's very similar to this. I don't know if it's question 26, but it should be around there, and you should just practice filling this out. Okay, you need a periodic table to help you out. So these are different isotopes, so we're talking about just single atoms of each one of these. Because of that, our mass number will be a whole number. And you can't rely on the average mass number or the atomic weight from the periodic table. Instead, again, these are just individual isotopes or atoms. Let's look at the very first line. It says that there's 9 protons. So I'm going to look on my periodic table, and that's fluorine. Make sure you spell it F-L-U-O-R-I-N-E. Okay, the symbol is F. The charge is 0, so that I know that means the number of protons equals the number of electrons. So because if I have 9 positives, then I will have 9 negatives. My neutrons are 10, and remember the mass number is protons plus neutrons. So I would get a 19. And you can look at the average atomic mass, and if you see that there on fluorine, it says 19.00. Fluorine doesn't have very many isotopes. Okay. All right, let's look at phosphorus. So phosphorus, finding on the periodic table, P is the symbol, and I can, looking it up, there's a 15 there, so that means there's 15 protons. The charge is also 0, so that means if I have 15 positives, I have to have 15 negatives. And I can get the mass number by adding it up. So 15 plus 16. All right, the next one. So I have number of protons is 26, and on the periodic table that's iron with a symbol of Fe. And then the charge is a 3. So remember, the charge has to do with electrons being gained or lost. Because it's a positive 3, that means 3 electrons left. So instead of having 26 electrons, I'm going to have 23 electrons. So remember, electrons are negative. So if they leave, it becomes more positive. My mass, I'm going to take 26 plus 30, and I'm going to get 56. Okay. And the last one, the number of protons is 16. Using the periodic table, that is sulfur. And it doesn't tell me the charge, but let's figure it out. So we have 16 positives, and we have 18 negatives. So that gives us, when you add it up, a charge of -2. So this is an anion, or a negative ion of a -2. And right above it is a cation, a positive ion. So go ahead and practice this in your homework. Charges of ions. So metals lose electrons and nonmetals gain electrons. When we look at the alkali metal family, they tend to form cations of +1. And your alkaline earth metal family forms cations of +2. Hydrogen's kind of a weirdo. It can be a +1 most likely, but there's some cases where it's a -1. Your transition metal family are various, but I do want you to know that zinc is a +2 and silver is a +1. Looking at the boron family, you should know that aluminum is a +3. And notice this series, +3, +2, +1 in a diagonal. So this whole boron family has a +3. Carbon family +4, nitrogen family, now it gets negative. So -3, so they gain 3 electrons generally in the nitrogen family. Some of these metals down here do some weird things, because remember, metals lose, so they won't follow that -3. But oxygen family, -2, halogen families are -1, and then our noble gas family tends to not form compounds, and so we say that nothing really happens. They used to be called the inert gases, but with a lot of heat and pressure, you can get the heavier ones to react, so they renamed them the noble gases. So you should memorize these are oxidation numbers, or the charge when it has gained or lost electrons. And you can see there's a pattern. Memorize this: +1, +2, +3, +4, -3, -2, -1, 0, going across. And then you should know this diagonal series. Aluminum is +3, zinc is +2, and silver is +1. Atomic weight measurement. So how can we find these isotopes? How can we see that some atoms are heavier than others? We can use something called a mass spectrometer. So the sample is vaporized, so we have a gas, and then there's a magnet that's involved. Also, the atoms are ionized, so they're turned into ions. And when those ions swing around this corner right here, when those ions swing around the corner right here, you're going to get some difference here. So your lighter ions, so this is a 35, they are going to whip around the corner more. Your heavier ones aren't going to be deflected as much. And because of that, this little detector right here, it can determine in a sample how much was the 35 mass and how much was the 37 mass. Then you get a printout that comes out. So it's just a machine. You put the sample in. Again, it ionizes it. It turns it into an ion. Then it uses this magnet and it's able to separate out the masses. So you get a printout that looks like this. So when you get something like this, you should be able to answer the following questions. First of all, how many isotopes of boron exist? Well, I can see 2 peaks, so 2. And what are their masses? So I have a mass of 10 atomic mass units and a mass of 11. And it says predict the approximate average atomic mass for boron. Now this chart is a little bit different. Do you see how this one is 100 and this is 25? So what they've done is they've taken the highest peak, and instead of keeping it as 100% and a portion of that 100%, they've made the highest peak 100. What? Why'd they do that? I don't know. This is just one way that they do it. So let's look at your the mass of 11. So we know that we have 100 out of 150 is that mass 11. So we see that 100 out of that 125, and we divide and multiply by 100, I get 80% is that mass 11. Well, then that means that 20% would be that mass 10. Well, you can find the average atomic mass now. So use your formula. So we have, I'm going to do the 10 first. So 10 times 20 plus 11 times 80. And remember, get rid of the percentages. And when I do my math, I get what? 200 plus 880. So we have 1080 and then divide by 100, and I get 10.8. So this is my average in atomic mass units. And we can look at boron, see how well we did. So when I look at boron, it says that it's 10.81. So we did pretty good. So this just adds on to what we just learned with figuring out the average atomic mass and now looking at mass spectrometer data. If it doesn't put the highest peak at 100 and just gives you a percentage, then you don't have to do this first step. You can just go straight to the second step and calculate the average. Okay, using mass spectroscopy, how does the data demonstrate direct evidence of different isotopes of the same element? Again, the isotopes that are lighter, they will move more, and the ones that are heavier won't move as much. And so what it does is the machine is able to separate out and figure out how many isotopes there are. Let's look at this one. What element's mass spectrum is represented below? So what's the element? We don't know. So first of all, we can see that there's 2 isotopes. And it does look like this one's 100, and then I'm just going to guess here, let's say 60. And so I'm going to do the same thing. So my first one, it's a mass of 185, and I'm going to multiply it by the percentage, which is 60 divided by 160. And I'm going to add it to the next one, 187. And it's 100 divided by 160. And so let's look at our numbers there. I think I won't put it in a percentage. I'm just going to multiply by 60 and divide it by 160. So this is 69.75. And then I have 187 times 100 divided by 160. I get 116.8. Let me add that up. So we have 186.6 is our average. And looking on the periodic table, see if we can find it. What's closest? Rhenium is 186.21. And it looks like the ones around it are heavier and really lighter. So that's my answer. That's the one that's closest. So I'm going to say this is